All right, so if we look at, I took glucose and I just shaved off all of the groups that aren't actually important yet, right? So what we're really focusing on here is the fact that this alcohol group on carbon 5 is going to act as a nucleophile, right? And it's going to come and attack that electrophilic carbonyl carbon. All right, this is these intramolecular cyclization reactions. Okay, so then again, here's our carbon 5, our alcohol group on carbon 5. This is just sort of now the structure's been kinked to show how that reaction can actually happen. Those two can actually get into kissing distance there. And notice that we have this group right here for carbon 6 that just remains kind of hanging out. Okay, and when you draw these Hawthorne structures, and again, we'll sort of go to that, but you'll see that they're always sticking up for these D sugars. And again, the D sugars are the ones that are actually found in nature. So, you know, whenever you're going to see these things, it's going to have that 6th carbon sticking up there. Okay. The last thing that was really important about this was what happens to the stereochemistry of this carbon here. Right? At first, when it's in this aldehyde form, it's just this sp2 hybridized, so it's in this planar shape, but it's going to become an alcohol group on that oxygen, and so there's going to be a certain stereochemistry involved. And you can't control which one you're going to get, right? So first of all, we had a special name for this carbon. This was our anomeric carbon. The anomeric carbon is the one that used to be the carbonyl carbon. Okay? And you can't control what the stereochemistry is going to be, so you're going to get a mixture of the alpha, which is when that OH group is pointing down, or the beta, which is when the OH group is pointing up. I don't have a good way to remember this, but that's just something that we have to know. So somebody come up with a silly like anagram for alpha is down, beta is up. We need a silly sentence there, like all dudes buy underwear or something like that, right? Some sort of thing so you can remember this fact that alpha means down and beta means up, right? Awesome, that one works. Okay, but that was really all about this slide that we've learned thus far. There's another whole element to this, which is how do we draw the Hawthorne structure? What do we do with those other side chains? But we're not quite there yet, okay? So everybody got this part so far, because that's where I'm going to kick off today, is sort of how we draw the rest of this structure, okay? Cool. So yeah, so now what about carbons 2 through 4? What happens there? All right, so when we're drawing our Hawthorne structures, again, just sort of note the frame. So I guess the first step is everybody should take a second to practice drawing yourself your hexagon, where then the bottom part gets fat. All right, this is going to be the shell of our Hawthorne that we're going to work with here.
Is it important to have that undershell?
The thick part?
Yeah.
Yeah.
Okay.
I mean, if you didn't thicken it, I don't know. It is because you'll always see it like that. If in your notes you want to be a little bit more sloppy, that's one thing, but it's important, to keep it consistent with what you think you're going to see all the time.
Okay.
And the real thing is that it's like they take the sugar and it's like instead of looking at it from the top, it's like it's twisted towards you, right? So you're supposed to imagine that this bottom part here is pointed out at you a little bit.
Mm. Okay.
And that thick portion is carbon 2 through 4?
Yes. And yes, except we actually we don't, for whatever reason with sugars, when they're we don't start labeling with the oxygen at 1. It's actually, this is carbon 1, 2, 3, 4, 5. Okay, so it's our anomeric carbon that gets to be 1. I know that this is different than how we numbered our oxycyclose. I didn't make the rules, I apologize, but that's just the fact of the matter, is that when we're talking about sugars, anomeric carbon gets to be carbon 1, just like it was when we drew our straight chain. So we got our shell. Awesome. Okay, so then the next step is we're going to put in that last carbon, carbon 6, and that is again going to be just sort of sticking up here. Boom, C2OH. Okay, so then we're going to get to our anomeric carbon here. Remember, we could draw it either way. We're going to get a mixture. If it's up, that is, of course, the beta, because they buy underwear. If it's down, that's our alpha. But that's the one that we sort of wouldn't know off the bat just by looking at this straight chain here, which way it would go, right? That's our anomeric carbon. It could be either direction. So let's just stick with this beta form for now. And the real question is, what do we do with carbons 2 through 4? So again, this is 2, 3, and 4. Which way do those functional groups go? So luckily it's honestly not as bad as the chair conformation sort of thing. It's a little bit more simple than that. If in your Fisher projection, the OH group is on the right, then it's pointed down. And if in your Fisher projection, the OH group is on the left, then it's pointed up. So if we just go through here, let's start with carbon 2. We'll go in order here. Can't really tell my left from my right. Okay, so this OH group is on the right, so that will be pointed down. Get to carbon 3, this OH group is on the left, so that will be pointed up. And finally, we get to carbon 4. Again, we have the OH group on the right, so that will be pointed down. Notice that there's no like equatorial business going on here. Okay, these Hawthorne projections, they're not the same thing as our chair conformations. All right, we'll sort of work in a second as to how we convert from Hawthorne to chair. But the Hawthorne projection is really trying to show us what type of sugar we have, right? So which direction is this OH group pointed? It's not like a very accurate picture of equatorial and axial. We'll see how that plays in here in a second, but it's either going to be pointed up or pointed down, not like pointed out at you or anything like that.
So right is down, left is up.
Right is down, left is up. Yep. So everybody do your best like Disco Steve pose. Left hand up, right hand down, boom. That's like our simple, silly thing to remember this, right? So boom. Left is up, right is down. Okay. All right, and that's really, I mean, I think that this slide got really big and ugly and scary, but that's what all this color coding was supposed to show you, right? These blue OH groups, they're all on the right, so they're all going to be pointed down, whereas that red OH group is on the left, and so that's going to be pointed up. All right, so this slide got like really busy because it was trying to hammer home like 5 different concepts at once, but that's really what they were trying to show you here. Cool, so we're gonna work on drawing these here in a second, okay? All right, so first of all, let's see, we'll build our cheat sheet. So we're gonna do the same thing, but for ribose. We're going to build a little cheat sheet here. First of all, when we're drawing the OH group, if the OH is on the right, what is that, up or down?
Down.
Down,
No,
and if it's on the left, that means it's gonna be up. Right, and if it's an alpha, the alpha stereoisomer, then it's going to be what? Pointed up or down?
up.
No, alpha's down. Unfortunately, I wish it
Alpha's
was.
down.
It would make more sense in my mind. But yeah, right. So that's why we have our all dudes buy underwear. All is down. Beta. I'm sorry. Alpha is down. Beta is up. Okay. Now here for ribose, we have, instead of a 6-carbon ring, we have a 5-carbon ring. And so what we're going to see is similar sort of cyclicization, except for instead of forming a 6-membered ring, we'll only form a 5-membered ring. All right, and in this case, it's going to be carbon 4. I'm sorry, let me pull something up real quick. All right, so this is going to be a similar sort of Hawthorne projection, but now we're going to be seeing it for a 5-membered ring instead of a 6-membered ring. Okay, and again for these, so first of all, is this an aldose or a ketose?
Aldose.
Right, so these are aldoses. We're only sort of covered the aldoses thus far. I wish I was more explicit about that at the beginning, but we're going to see here in a second the ketoses. They're basically the same thing, but the structures you get are a little bit different on the other side. For the aldoses, again, it's always going to be that last asymmetric carbon that you're worried about. Okay, so here it's the alcohol group on carbon 4 that's going to act as your nucleophile. The electrophile is, of course, going to be
the carbonyl carbon.
The carbonyl carbon. And we'll worry about what happens with these alcohol groups here in a second. Let's just focus on drawing our 5-membered sort of closed ring for now. So again, if we sort of look at this where this thing is kinked into the right position, all right, so again, I've sort of left off what's going on with carbons 2 and 3 for right now. But the bottom line is carbon 1, which we call our what? Right now it's a carbonyl carbon, but it's about to be a anomeric carbon, yep. We have our electrophile carbon, and again, that's going to be attacked by the alcohol group that's on carbon 4. And so again, that last set, that sort of tail here, is just sticking up in our Hawthorne projection. Okay. And then we have the 2 different possibilities that we can get. All right, take a second and see if you can't tell me which one of these is alpha and which one's beta.
The one on the left is alpha. The one on the right is beta.
Yeah. All right, so again, you're just looking at which direction that OH group is pointed on your anomeric carbon. All right, and then the rules are the same when we had our 6-membered structure. So now let's just go back and fill in where these OH groups are going to be positioned. Both of them are actually on the right. So I do my little pose. Cool.
Where does the hydrogen on the nucleophilic oxygen go?
You're gonna have a proton transfer from this oxygen to this oxygen.
Oh,
right.
Right. Okay.
This guy becomes an alcohol group. Which means that I think this would be considered a tautomerization. Heyo. Because we don't actually change our molecular formula, just the connectivity. All right, anyways, doesn't really matter. Okay, but this is how we get to our Hawthorne of now a 5-membered ring. You see, it's really not that much different. Again, I guess, you know, start with your shell. Now you just have the OH group at the top, and then the bottom part is a little bit thicker, right? But that would sort of be my strategy here with drawing these things, is start with the shell and then go through and decorate things as, you know, as it's supposed to be. We'll practice going from what is this sort of Fisher projection to Hawthorne here in a bit, but we got to learn a little bit more about these closed rings, some sort of terminology here first. All right. 5-membered rings are called Pyranoses. All right, so any sort of a sugar that's closed into a, I'm sorry, I think I said 5. 6-membered ring is a Pyranose, and any sugar that's closed into a 5-membered ring is a Furanose. Okay, and then that actually changes what we call the sugar a little bit. If this was in its straight chain Fisher projection, this would have been, well, it wouldn't have had the alpha, but it would have been D-glucose. Since it's in its closed ring form, the correct name is now alpha D-glucopyranose, right? So we're going to replace the ose with pyranose. I should keep the O for some reason, but glucopyranose sounds weird maybe.
So just to make sure I have this right, the alpha or beta is determined by the alcohol group on the anomeric carbon, and the D and L is determined by the very last carbon, the last asymmetric carbon.
The last asymmetric carbon, which is in this structure, would actually be this guy here.
Okay, gotcha.
And it's honestly, like, we talk about L sugars because you can, but like every single sugar you will ever see in your entire life will be a D sugar. All right. I mean, there's a reason why we're sort of like only kind of focusing on those D sugars. And again, that's because nature has this preference for them for whatever reason. But yes, and then I guess I should have erased this alpha here, because when it's in its straight chain, it doesn't have an alpha or beta notation, right? It's only when it is in that closed ring form that it would be alpha or beta. So here, this sugar is D-ribose. All right, so now that it's in its closed chain form, is it alpha or beta?
Alpha.
So this is alpha now because that OH group is down. And now it goes from being ribose to ribofuranose. All right, so
just hypothetically, how would you know from this representation of the compound if it were D or L from the CH2OH?
Yeah.
Oh, because it's one's on the right, one's on the left.
Yeah, this guy would be pointed down if it was an L sugar.
Gotcha. Okay.
All right. And again, I'm not going to make you memorize all the different sugars. I think that's just ridiculous. But you absolutely should know terminology pyranose and furanose, right? So pyranose just being a sugar that's in its closed 6-membered ring form, furanose being sugar that's in its closed 5-membered ring form. And then let's actually pick this word apart as well, because we call these cyclic, I've been calling it its cyclic form. It's actually, like, if I were being really good about it, it's called a cyclic hemiacetal. Okay. What makes this a hemiacetal is this set of bonds here. The fact that it goes R-O-C-O-H. right? It's not a full acetyl because this is an OH over here. So the fact, like hemi meaning half, it's a half acetyl because of this linkage right here, okay? But we will get into, just not being able to spot whether it's hemiacetyl or acetyl is going to be something that's important. And again, the hallmark of a hemiacetyl is the fact that it has a free OH group on that anomeric carbon. All right, we're going to see that we're going to link sugar molecules together through that anomeric carbon. So, all right, so now let's do it. Now we're going to talk about the ketosis. They can form Furanoses and Pyroses as well, right? 5- and 6-membered rings. Again, who do we think is going to be the electrophile?
Carbonyl carbon.
Carbonyl carbon, awesome, right? So here we still have this guy acting as the electrophile. And you can actually get with the same, so if we just want to look down at the bottom here, you can get a Furanose and a Pyrose from the same sugar, okay? So this guy up here, this is fructose. It's the most common sugar found in fruit, so that's how that gets its name. And this can either form a 5- or a 6-membered ring depending on which carbon reacts, okay? You can either have 1, 2, 3, 4, 5, 6. You can either have the OH group on carbon 5 reacting, so that would form a Furanose, or the OH group on carbon 6 reacting, that would form your Pyranose. Okay. So let's go through and see if we can't draw what these are going to be. So first of all, we of course, in our pyroses, we have the alpha and beta. That's just going to be what happens to that anomeric carbon, whether the OH group on there is pointed up or down. We can't control that. These do look a tiny bit different though, so let's go through and see what would happen. So let's start out actually with these pyranoses here, because they look a little bit different than what we're used to seeing. Okay, so again, your Pyranose is going to form when your C6OH reacts. So what I'm going to do now is go through and ignore everything else, and we'll worry about that later. I'm just going to connect this guy to this guy. Okay, now one of the things to notice is that previously our electrophilic carbon was carbon 1. So we didn't really have any sort of thing to worry about there. Here, you have this group on top of your anomeric carbon as well. So your anomeric carbon is going to have an OH group as well as this other group sticking off of there. Right, so now there's going to be 2 groups pointing out of that anomeric carbon. One of them is going to be the newly formed OH group, newly formed alcohol group. But now because it's a ketose, we have this existing carbon 1, this CH2OH to worry about as well. So let's go through and, right, so here's my anomeric carbon. Let me get rid of this. All right, so that's what we got so far. If we know that the alcohol group on carbon 6 attacks that carbonyl carbon, this is sort of what we have so far. And this would be in the alpha form. So everybody take a second and draw me what the beta form would be. Cool. All right, so notice here, two things to point out. So first of all, looking at our anomeric carbon, right? That's this guy here, carbon 2. Again, because it's a ketose, now there are 2 groups coming off of that. You have your OH group. We had to worry about that last time as well, and that could be either pointed down for the alpha form or up for the beta form. You just also have this other CH2OH group on carbon 1 as well, on your anomeric carbon. Let's call it anomeric carbon. Okay. The other thing to point out that was a little bit different from what we're used to seeing is now carbon 6 is naked. There's no OH group sticking off of carbon 6, right? Because carbon 6 was the end, the terminal carbon in our straight chain, right? So there was no additional CH2OH group sticking off of that. So it's just sort of naked now. All right, so 2 sort of key ways that these are like visually going to be different looking rings. Okay, so then lastly, we can go through and figure out what the heck should be happening with all of our other side chains here. Everybody take a second and see if you can't fill that in on your Hawthorne projection, given what we just learned in the last slide. All right. Huh.
If it was on the left, would it be written from would it be written as like HO H2C instead of CH2OH?
You mean for this thing here, could you have it like, and then it was HOH2C?
Right, but I'm more talking about the oh yes. Is that
Yeah,
is
that's
that
fine. That's legit.
perfect? All right, thank you.
Honestly, it looks like a little weird to look at, but whatever.
Yeah.
It's all there. All right, so like disco Steve pose, left hand's up, right hand's down, right? So carbon 3, which is this guy, it's on the left, so that should be pointed up. Check. And then the other 2, carbon 4 and 5, 4, 5, those are on the right, so they should be pointed down. And again, that's true whether it's in your alpha or your beta. All right, so then again, now we're going to do the same thing, but we're going to create a Furanose. So we're going to create just a 5-membered ring, but we're going to be starting out with our same sugar, fructose. And again, here we're going to go, our Furanose is formed when the C5OH reacts. Right, so again, our electrophile is of course going to be that carbonyl carbon, but now it's going to be our C5OH group that's going to react, right? That or that's going to be our nucleophile. Okay. So again, what I'm going to do, and I'm going to sort of let you guys loose here, but again, strategy, ignore what's going on in the middle. All right. We can figure that out afterwards. Okay. Just work on closing your ring when you have this attacking that. And so everybody take a second and see if you can't get, pick alpha or beta. I don't really care. But starting with that shell, that 5-membered Hawthorne structure, see if you can't start filling it in with what you would need for this ring closure here.
I put the carbon-6 alcohol on, like, outside of the ring on the, it's like carbon-6, right? Off of carbon-5.
Yep. Yeah, it looks a lot like the past ones that we were drawing.
All right, cool.
Yep. So I'm gonna give you guys another like minute and a half on this, and then we'll walk through it. All right, so let's go through it here. Again, let me just label this. 1, 2, 3, 6. Okay. So again, I'm going to start off with my shell here of my Hawthorne structure. Where's my anomeric carbon? Left or right?
The carbon on the right.
Your anomeric carbon is sort of always going to be positioned here. The whole point of these Hawthorne structures are so that when you look at them, you can very easily tell what sugar you have. So, you know, we're kind of used to like seeing structures where you can draw them in multiple different ways. The whole shtick here is to try to keep it in the same sort of standard format. So when you look at it, you know exactly what you're talking about, right? So that carbon, your anomeric carbon, is always going to be the one that's directly next to the heteroatom on the right. And so if this is the alpha form, the OH group is going to be pointed up or down? Down, yep. And because this is a ketose, I still got this other CH2OH group to worry about that's on my anomeric carbon, right? So if my OH group is pointed down, that means that guy's got to be pointed up. Okay, so sort of step 1. So now 2, 3, 4, 5. Notice that on carbon 5, I still have this CH2OH group. Unlike when I made my 6-membered ring and it was like a naked carbon there, that's not going to be the case for my 5-membered ring. I'll still have that, and it's going to be pointed up. Convention's always going to be for the D sugar that that group is pointed up. Okay, so then if I were to do my beta, I would see something very similar, except now my OH group on my anomeric carbon and this alcohol group have been switched. So then lastly, we'll go through, and now we can worry about what happens on those carbons in the middle using our Disco-Steve rule of if it's on the left, it's pointed up. So that means carbon 3, those hydroxide groups should be pointed up. And if it's on the right, it should be pointed down. All right, so let me just sort of rewind back real quick and show everybody previous slides, right? We learned about what? There are 8 different types of hexoses and 5 different types 4 different types of pentoses for your aldoses, right? As well as a plethora of different ketoses. So these are, you know, if you're trying to practice your Hawthorne structures, just pick one and convert it to that Hawthorne structure, right? So there should be, this is just like an easy thing that you can practice. The Google machine works great for verifying that you have it correct. But yeah, so if you are looking to do some practice for drawing these sort of things, just pick a random sugar and see if you can get it into its correct Hawthorne structure. Where are we at? Okay. All right, so now we got how to draw those. Now, unfortunately, we have a bit of a bigger pain in the ass problem here, which is, everybody remember these guys?
The chairs.
The chairs. Yeah, unfortunately, they're going to rear its ugly head. The purpose of the Hawthorne isn't to show actual like arrangements of atoms in space, right? It doesn't convey a correct 3D image. It just helps you figure out what sugar you're talking about quickly, right? So the Hawthorne to the Fisher, or the Fisher to the Hawthorne is meant to be an easy process. How these things are actually sort of shaped, how they're actually arranged in space is the chair. All right, so now we got to work on going from Hawthorne to chair, right? We did Fisher to Hawthorne. Now we got to go from Hawthorne to chair. Okay. Let's actually zoom in on this generic guy here, right? So there are different positions that are labeled here as either circles or triangles, right? In my chair projection. The circles are meant to represent what type of position? Does anybody remember what we called these?
Equatorial and axial.
Yeah, so which ones are the circles?
Those are axial.
Right, so if they're pointed either straight up or straight down, those are your axial positions. If they're pointed out, those are going to be your equatorial positions. And does anybody remember what's more stable, to have a big bulky group in the axial position or the equatorial position?
Axial.
Axial.
Equatorial.
Equatorial, right? Big groups want to be pointed out of the ring, right? The axial positions are much closer to one another. So equatorial is where we want to put our big group. Now, the pain in the butt thing about these were, well, first of all, I guess just drawing them, right? So first, if we want to just review how we did that, right? So you start by doing 2 parallel lines pointed. Doesn't really matter what direction you pick, but mine are going to be sloping down to the left. And then you got to meet them at a point. That was terrible. I'm gonna get rid of my cheat sheet real quick. All right, so now working just with the skeleton structure, this thing here. Take a second and tell me where, drawing the axials that are going to be pointed up. Right, some axial bonds are pointed directly up, some of them are pointed directly down. So which carbons have axial positions that are pointed up?
The ones on the left.
So it's not as, everybody take a second. It's not quite that simple though. It's going to be like every other one, okay?
Directly up, those would be the carbons 1, 3, and 5, I think.
Well, I don't know. It depends on how you number, but bottom line is the ones that meet at a point, right? If they meet at the tip of a triangle, then that means those axial positions are pointed straight up. And it's every other one, right? If they're pointed at a trough, so at the bottom, a triangle that's upside down, those will have the axial positions pointed down. All right, the last thing that I want to review about our chair structures here are like with regard to cis and trans. So actually, let me get rid of most of these. I'll even keep a little reminder there. So this structure here, all right, talking about this guy here, are those two substituents cis or trans? Are they on the same side or opposite sides?
Cis.
Well, one's equatorial down and one's equatorial up.
So
They're
both
trans.
equatorial, right? Axial's either down or up. Equatorial is always just out. But they're going to be trans, right? So if we fill in what the other substituents look like here, right? These guys are on the same side. So if both of them are equatorial right next to each other, then they have to be on opposite sides. Remember, you kind of had to like divorce this concept of cis and trans from axial and equatorial. They're not synonymous with one another. Just because you know they're both axial doesn't mean that they're both cis or trans or vice versa, right? It's a little bit more complicated than that. So this is kind of the name of the game that we're going to have to play when we're converting here. Figuring out whether they're on the same side of the ring and thus whether it's going to be axial or equatorial. So let's, we'll go through and do this on our own. Should have erased this. Okay. So again, this is all going to be about converting your Hawthorne to chair. All right, so we've successfully gotten our Hawthorne structure. Awesome. Okay, step one is again going to be to draw the frame of your chair. Put the oxygen in that top right corner. Okay, you could draw your, you can draw your chair conformation in a million different ways. Frickin' standardize it, right? We don't need to see this thing from every different side. We're trying to get out of here alive, right? So just pick one way and do it always that way, and it'll make life a little bit easier. And the starting point for how we figure out where everything else is we have to put this big group in the equatorial position, right? So in the case of this particular, what would be glucofuranose or glucopyranose, we're going to stick that carbon 6 in the equatorial position. Okay. So then we're just going to go to every other carbon. Right, so now let's look at what happens with carbon 4. Okay, so now I'm going to compare the position of this group to the position of this group here. Are they cis or trans? These two groups that I've identified in blue here.
They're cis.
Trans.
Yeah, they're going to be trans, right? Because if it was cis, that would be my OH group also sticking up. So this would be an example of a cis right here where both of them are pointed up. So honestly, on your Hawthorne projection, cis and trans is easy. If they're both pointed up, it's cis. If one's up and one's down, it's trans. right? The Hawthorne projection is actually a little bit easier to understand than the frickin' chair is. Unfortunately, the chair is the most accurate for the 3D structure. That's why we got to worry about it. So in this case, they are going to be trans. And so that means that the OH group also has to be equatorial on position 4. So the easiest thing to do is just to continue to sort of like jump down the line. So now I'm going to compare carbon 4 and carbon 3.
Those are trans.
Those are going to be trans. And so again, it's, if you haven't quite gotten your chair structures down, it might not be obvious as to why this is, but that means that they're also both going to be equatorial. Sometimes it helps to sort of draw in the other positions to see what it would be. Right, and you can convince yourself that way that these are indeed trans from one another, right? If it was cis, then that OH group and its neighbor should be there. That would be being on the same side of the ring. That's why I think that being able to start with the naked chair, like we did up here, and then stick in which way the axial groups are pointing are incredibly important. Equatorial is easy, they're always pointing out. But is the axial group pointing up or is it pointing down? If you can't figure that out for a given carbon, it's going to be really hard to tell whether trans means axial and equatorial or all that business, right? So starting out with being able to get to this sort of chair with putting in the axial positions, that's kind of the most important part. Okay. So just on that, if I'm on carbon 2 here, which direction is my axial position pointing?
Is it down?
Not down.
It's pointing up.
It's pointed up. And why is it pointed up, Sam? Because it wasn't down.
Because that corner's pointing up.
Yeah, exactly, right? So you're looking at whether the carbons meet at a point like this, axials will be pointing up, or if they meet at a point like that, right? I can't really do it on my video very well, but yeah. All right, are they at a peak or a trough? So this would be where my axial is. So then I'm going to look at carbon 3 compared to carbon 2. Are they cis or trans?
Trend.
Trans. So then that means that this should also be equatorial, right? Because cis would be both of them, right? If they're two carbons next to each other, then cis means one of them's axial, one of them's equatorial. It's honestly something that you just want to practice going through, going from Fisher to Hawthorne to chair. Do that a few times and you'll have it down. This isn't one of those things that you see it done and you're like, oh yeah, perfect, makes sense. There's a lot of like nuance here as to what's pointed where that you just kind of got to walk yourself through. We'll do another example all the way through here, but again, I feel like just listening to me talk about it isn't going to be enough. You guys want to run through one example by yourselves, practice one example by yourselves. And then lastly, now we're going to go through to our last group here. So first of all, this carbon 1 here, axial position is up or down?
Down.
It's at a trough, so that axial position is going to be pointed down. And now if I'm comparing carbons 1 and 2, that's cis or trans.
That's cis.
So they need to be on the same side. Right, so here's our first example of an axial OH group. All right, but that's kind of, yeah.
Could you explain again why the carbon 2 is up?
Is up and it's not up, it's equatorial. But yeah, so let's just draw in the other possible positions here for both carbons 3 and 2. And then, whoops. And then let's erase this and this. Okay, so it's kind of like this step-by-step process where you have to start with like this guy over here and then fill in everything. Okay, it's hard to just look at it and jump from there. But if we start, sorry, let me erase some of my markings here. Okay. So let's say I got to here, okay? I know that my OH group on carbon 3 should be there. All right, that we already have. And then I'm gonna look at my Hawthorne and I see that these guys, if I'm comparing carbons 2 and 3, they have to be on opposite sides, right? They're trans from one another. So now I'm gonna go to carbon 2 and I'm gonna draw in the two possible positions that I could have. Either my axial, which in this case is pointed up because it's at a peak, or my equatorial, which is sort of always pointed out there. And I'm gonna make sure to put the OH group on the opposite side of where it is on carbon 3. If I put the OH group here, that's on the same side as where it is in carbon 3. Right? And by same side, I mean they're both kind of like on the top. This is axial down here. It's in this equatorial position, so that would be the same side as this. Right? But I know that given my Hawthorne projection that it's not on the same side, so that's why I have to put it here.
Okay, got it.
Right? And again, it's like, it'd be so much easier if cis and trans and axial and equatorial were like directly related to one another, but they're not. It's just a little bit more complicated than that. All right, so let's just do another one from the very beginning here, okay? We're gonna take this random 6-membered ring here. I'm sorry, this random hexanose 6-carbon sugar here, and you guys are going to convert it to the correct Hawthorne projection for me. And let's just have everybody do the same thing. So let's go ahead and do the beta. Actually, I shouldn't have given you that even. Well, damage has been done, but right, this, you want to convince yourself that this is actually sticking up here on carbon 5, given the sugar that we're starting with. All right, so first, if we are doing the beta, then which direction does the OH group on my anomeric carbon supposed to be pointed?
Up.
Up, up. So can automatically, just because I told you it was going to be the beta, put that there. And then is there going to have to be this CH2OH on that anomeric carbon as well?
No.
Why not?
Yes.
No, Eric's right, but why not, Eric?
It isn't because of the way it is.
That is flawless logic for sure. One of the things that we can definitely do to convince ourselves, just like always, count carbons, right? So if you go through and count carbons, that wouldn't also work. The other thing is this is an aldose, not a ketose, right? It's only with the ketoses that you have that extra group. With your aldoses, you don't, right? Because again, it's your carbonyl carbon, that's your anomeric carbon. They're one and the same, right? So you just look at how many bonds it has. But so in this case, we wouldn't need that down here. Whoops, ignore that. Okay. And I guess first thing I should have done is go through and say that I'm going to ignore all those guys there, right? I'm going to ignore what's going on all those carbons in the middle. All I really know for now is that that alkyl group or hydroxyl group has attacked my carbonyl carbon. And again, as convention, we have this last 1, 2, 3, 4, 5, 6. Carbon 6 is pointing up in our ring as well, right? Because it's a D sugar. 5. So now the question is carbons 2, 3, and 4. What the heck is going on there? So now we can look at our what's going on there. On carbons 2 and 4, they're on the left. So that means they should be pointing
up,
right? Just goes deep. So 2 and 4. On carbons 2 and 4, they're pointed up, and on carbon 3, it's pointed down. Whoops. So let me clean this up. All right, but that would be the Hawthorne projection for the beta form. This is beta D. Ido, what?
What?
The sugar, if we're going to name it in this form here, it's beta D Ido.
Furanose.
Furanose. Pyranose. Furanose. I actually don't know. It's a really unfortunate thing with chemistry is that you tend to read these words a lot more than you hear people say them. So like sometimes I have no idea how crap's pronounced. I just know how it looks on paper.
I thought, but it's a 5-membered ring. I thought 5-member was Furanose.
Is it a 5-membered? We're not talking about the carbons in the ring. It's how many members of the ring as a whole.
Oh, okay. Gotcha.
Yeah. Yeah, so right, and just to review, right? This is what our 5-member, what our Furanoses looked like. 1, 2, 3, 4, 5-membered rings. All right, so now we have this pain in the butt complicated step of going from our Hawthorne to the chair, okay? So first steps first is I'm gonna put that big bulky group at carbon 6 in the equatorial position. Now for me, what I would go in and do is in your skeleton of your chair, figure out where the axials are. Which way are the axials pointed? So let's just do this together here. I'm going to label carbons. Let's do that in red. So this is 1, 2, 3, and 4. 5 we already got. So carbon 1, axial should be down or up?
Down.
Down. And then from there it's easy, right? Carbon 2, Going to be up, 3, down, 4, up. Cool. So everybody take a second and see if you can't go from our Hawthorne to the chair. I guess I can put that. This guy's pointed down. All right, so let's go through it. Again, the easiest thing to do, in my opinion, is to start with what you know, which is that carbon 6 is in the equatorial position, and then go down the line from there, right? So now I'm going to look at carbon 5. Are those on the same side of the ring or opposite sides?
The same?
Yeah, so they're going to be on the same side, right? Again, in the Hawthorne projection, it's pretty straightforward. They're both pointing up or they're both pointing down. They're on the same side. If they're switched, then they're trans. The hard part is, where do we put that on our chair, right? So does that mean that our OH group will go in the equatorial or the axial position on carbon 4?
Axial?
Yeah.
Why would that be?
So again, it's what you want to do is sort of look at the two possible choices, right? That's why we drew in all those axials to see what one of those choices are. So the other choice is here, Carlo. So I got two choices. It's either going to go there or there.
Right.
And so which one is going to be on the same side as this group here?
Okay.
Right? So if I put it in the equatorial position, whoops, sorry, don't pay attention to that. If I put it in the equatorial position, they're both equatorial, but that doesn't mean that they're on the same side. Right? So that's what I say. Unfortunately, axial, equatorial, cis-trans are just kind of different concepts.
But you want them to be on the same side for each one, but that sometimes that means just switching from equatorial to axial or vice versa.
Yeah. I mean, I feel like you can say it a few different ways and it might start to sound like word salad, but yes, if you're talking about two carbons that are next to each other and they're cis, that means one of them's axial and the other's equatorial. Yeah, and fortunately for this, like when we talked about the chairs before, we weren't always talking about carbons that were directly next to each other. Sometimes they were 3 removed or 4 removed, and that was even another layer of complication. The only like saving grace here is that every single one of these carbons has a substituent, so we can kind of go down the line, and it makes it a little bit easier. So now we're going to jump down the line again. So let me just get rid of. There we go. Here's my OH group here. So now again, jumping down the line, looking at carbon 4 compared to carbon 3. Are those cis or trans?
Those are trans.
Those are trans. So if I'm looking at carbon 3, is it going to be axial or equatorial?
Equatorial?
No, it'd be axial.
It will be axial, right? So again, just look at your two positions, right? If it was equatorial, those would be on the same side. So that's why now we have to put this guy. Boom. All right, again, we can draw in both positions for everything just to make it a little bit more helpful. All right, now I'm going to compare carbons 3 and 2. Same side or different sides?
Those are different sides.
Different sides.
And so what am I going to get for on carbon 2? Equatorial or axial?
Equatorial.
Axial. Axial.
God damn it.
Axial.
You you're getting it like 50% of the time. That's pretty good. But yeah, right. And again, you just want to convince yourself that these two groups, these two axial groups, are indeed on different sides. They are indeed trans from one another. All right, and then this is going to be another friggin' curveball here. What happens, sorry, put this guy in again, OH. So now when we look at carbons 2 and 1, those are going to be same side.
Same side.
Those are the same side.
Those are the same side. So what is my carbon 1, axial or equatorial?
Equatorial.
Equatorial.
Nice.
Yep. Okay, I think I'm starting to get it now.
It's a pain in the ass. I'm not going to lie. I mean, those chair conformations are, once you get it down, it's really not too bad. But if you don't literally put pencil to paper and draw and go through the thought process, you're never going to get it. It's not something that you're going to get by watching somebody else do it. It really is kind of a tricky thing here. So again, just go back to that page with all the different sugars. Pick one, go from the Fisher to the Hawthorne, and then the Hawthorne to the chair. I mean, the good news is we can only ever do this for the Furanoses, right? We don't have a chair conformation for 5-membered rings that we got to worry about. So dodge that bullet. But yeah, so any 6-membered sugar, you want to be able to convert to this chair conformation. And we'll wrap it up here, but let me just show you why so we can sort of see where we're going. When you start joining sugars together, you look at them in their chair conformations, right? So these Hawthorne projections are great for looking at just a single sugar. When we start talking about polysaccharides, they're going to be in their chair conformation. Now, good news is I'm not going to make you draw a whole freaking polysaccharide or anything crazy like that, okay? But we do need to be able to look at them and see what type of linkages there are. That's the last key to this chapter that we got to do is looking at a polysaccharide. Can we see if there's a alpha or a beta linkage, 1,4, whatever. That's what we'll be doing next time, okay? But we do got to be able to look at these types of structures and make some sense of them, okay? Again, today, moral of the story, right? So last class was all about getting through those 5 different types of reactions that we see with our sugars. So make sure you got those reactions. Today is all about Fisher to Hawthorne to chair, right? You want to make sure that you can do that. Okay? Cool. Any questions?
Is there, at the risk of, my classmates hating me, is there homework for this chapter or?
Oh yeah, there is homework for this chapter. Yeah, it's not gonna be too bad, but there will be homework. I'll post that tonight as well. Yeah, we got to finish up our homeworks. They won't be too bad. And actually, I'm flirting with the idea of giving you guys some sort of like a open book take home exam kind of practice thing next week that you can do for some as a mini assignment as well. So basically just to get some practice problems in. It will be optional. If you don't do it, it won't count against you. If you do it, it will count for you. But just to get some practice in there on that.
Will it be like a cumulative practice?
No, it'll be specific to this chapter. Because, basically the logic is you have your old exams to study for everything else, but you won't have that same type of thing for this. So, but it'll be open book because there will be like sugar names that you'll be allowed to look up. Because again, I think it's ridiculous to make you guys memorize sugar names. But yeah, so you'll have that next week. And I'll give that to you next week, and it will be due before the final exam, but during that finals week. Right, so you guys only have 1 more week of new information that you have to learn. You guys are like almost through this brutal ass process of organic chemistry. So congratulations. Yeah, but yeah, we do got a little bit more to go here. So finish strong. All right. Yeah. Cool. All right. So yeah, I'll get you your homework and I'll get that posted. And yeah, I won't make it too crazy. All right. All right, y'all, well, enjoy your weekend.
Thank you. Thank you.